Good morning. So in today's lecture, we will look into the application of the induction type instrument for the purpose of measurement of energy, that is as an energy meter. Okay. Now it's obvious that the energy consumed is the work done over a period of time. That is, it is the integral of power integrated over a period of time. Okay, and since it is an integrating quantity, since the energy consumed is an integrating quantity, the energy meter should also be an integrating instrument. That is, it is not supposed to give the instantaneous value, but it is supposed to give the integrated value over time. Okay, and for this purpose we would be using motor meters instead of indicating instruments. Okay, and it doesn't matter whether we are doing it for AC circuits or DC circuit. Energy measurement or energy indication should be done using motor meters, which would have a rotor that is whose spins continuously and whose speed of rotation is proportional to the power being consumed, and therefore the number of rotations over a time t would be proportional to the energy consumed in the time t. Okay. Now, the motor meter, as I said earlier, is an integrating instrument, and in any integrated instrument, there is a rotor, and you would have one or more stators, and you have a retarding mechanism, and the speed of the rotor would be proportional to the instantaneous quantity being of the input. That is, in this case, if you are talking about the energy meter, the instantaneous quantity is power, thus the speed of the rotor is proportional to the power. And another thing to notice is that you have a retarding mechanism. Okay, you have a retarding mechanism, and you don't have a control mechanism. So you have a mechanism which gives a torque that is proportional to the speed, so that the speed can be kept in control, and you don't have a mechanism that gives a torque that was proportional to the theta of the deflection, as we had in the PMMC or all the other instrument, PMMC, moving iron, and the electrodynamometer instrument. You had a control spring, and that was giving a torque that was proportional to theta. In the integrating the motor meters, you don't have such a mechanism, you don't have a control mechanism, you have a retarding mechanism only. And you have this concept of a meter constant, which would indicate the number of revolutions made per the integral unit. That is, in this case, in the case of an energy meter, that is the number of revolutions per kilowatt hour, and that would be the specification of the meter. This meter constant will depend upon a number of parameters of the instrument, of the meter, and it congeals many different parameters of the instrument, and from the user point of view, this is the only constant that is of relevance. Moving further, as I said, that you have a retarding mechanism or a braking mechanism in the integrating instrument, and the speed of the moving system is thus controlled by this braking mechanism. Typically, this braking mechanism is placed on a part of this moving system. So let us say in case of an energy meter, you have an aluminum disc that keeps on rotating. As we have seen in the induction type instrument, you have an electromagnet being excited by the current that is being measured, and this interacts, causes eddy currents in an aluminum disc, and this aluminum disc rotates. And in case of in induction type ammeter or a voltmeter, what we had a control spring here. Now in case of this motor meter, instead of control spring, what you do is that you place this same you forego this control spring, and instead you place a permanent magnet on one side of this disk. And so when this disk rotates, it interacts with this permanent magnet, inducing eddy currents, and that gives a braking torque. So if this is rotating in one direction, there is a braking torque, and when this rotating torque and the braking torque balance out, the speed stabilizes, and this speed is supposedly proportional or directly proportional to the power that is being consumed instantaneously. Okay. Now, induction type instrument can be used as an energy meter by making use of eddy current damping as the control torque, or actually the damping torque. Okay, and there is no control spring, and a constant rotation rate is indicative of the power consumption, and the number of rotations is indicative of the energy consumptions. Now, in case of the use of a induction type instrument as an energy meter, you would have two electromagnets. Okay, one of these electromagnets would carry a current that will be proportional to the voltage. The other electromagnet will carry a current that is proportional to the current, so to the load current. So one will be proportional to the load voltage or the supply voltage, and one would be proportional to the load current. And this would obviously produce two fluxes, and the interaction with these two fluxes is going to give us an indication. Okay, so typically in case of single phase induction type watt hour meter or energy meter, you would have these four subsystems. One is the driving system, which would be powered by this voltage and current. Okay, one is this moving system, which is this aluminum disc that rotates, and you would have this braking system that gives the braking torque, and the registering system, which gives us the display or converts this rotation into an equivalent display that gives the readout of what is the watt hour, or what is the energy being consumed. Okay, now let's look at each of these system in sequence. So first look at the driving system. As I said earlier, there are two electromagnets with the core made of steel laminations to reduce loss in the core itself. Okay, and these two coils are connected in a manner that you would have the current coil being connected in series to create the series magnet, and the pressure coil is connected across the supply voltage, and that forms the shunt magnet. Okay, you would have additional adjustable copper sharing bands placed on the shunt coil to cause some lag in the flux. So to cause further lag between the flux in the pressure coil, so if this is phi p, you would have the shading bands, which will increase the uh, phase lag between V and phi p. And we will look exactly into this mechanism later in this presentation. Okay, and the purpose of this shading band is so that this V becomes and this phi p are in quadrature, and I and phi s would be in phase. Okay, the moving system would consist of this aluminum disc that is mounted in this on a shaft and placed in the gap between these two magnets. And this shaft, in order to reduce the friction, the shaft is dual pivoted, and there will be a rack and pinion mechanism that engages this shaft to the registering mechanism. Okay, the braking system would consist of a permanent magnet kept at the edge of this disc in a manner. Okay, and this position is adjustable so that the braking torque can be increased or decreased as per requirement. Of course, the registering or counting mechanism would be a set of gears and connected to a display mechanism that will eventually display the amount of energy being consumed in watt hours. Okay, now coming to the theory of the operation. So as mentioned earlier, the supply voltage is applied across the pressure coil. The pressure coil has a large number of turns and is highly inductive. So it has a large value of Z, and Z is highly inductive also. So it's a high impedance circuit. It's and with a high value of inductance also. Okay, now regardless of whatever may be the impedance, it cannot be a purely inductive circuit. So what would happen is that the current in the pressure coil would lag the voltage in the pressure coil. So VIP would lag VP by an angle, by a large angle delta, but delta is not equal to 90 degrees. So it cannot lag by 90 degrees exactly. So it will be slightly less than 90 degrees. Okay, and this anyway would this would produce a flux phi p, which is in phase with IP. Okay, and this, the lag is delta, but the delta is not equal to 90 degrees, that is known. Okay, now this flux phi p is going to induce a eddy EMF EEP in the disc, in the aluminum, in the moving disc, and that will lag this phi p by 90 degrees, and there will be a current IEP produced in the disc. This is the eddy current, and this eddy current will lag further by, let us say, an angle gamma. Let's look at these things again later. And on the other hand, the load current I, which flows to the current coil, produces a flux phi s, which will be proportional and in phase with the load current. Okay, this in turn will produce this flux will in turn will produce an eddy EMF EES and an eddy current IES. Okay. Now we have seen that there are lots of parameters. Let's look at a phase diagram to understand this better in the next slide. Okay, and as we have seen in the case of the induction type instrument, okay, these fluxes, so phi p will interact with the eddy current produced by the current coil, and phi s will interact with the eddy current produced by the pressure coil, and they will produce torques, and the effective torque is a resultant of these two torques. Okay, so this is the schematic of it. Okay, and generally the way the coils are wound is in a manner such that these two torques are in opposition. So you would, if this is tau 1 and this tau 2, the effective torque is tau 1 minus tau 2. Okay, now let's look at exactly what these particular torques would turn out to be. As we have seen earlier, as a revamp, so we have V as the voltage, supply voltage, and you have phi p which lags V by an angle delta. Phi p is in phase with IP, the current through the pressure coil. Okay, and this is producing a EMF EEP, an eddy EMF, and there is another current IEP that is lagging this by a angle of alpha. Now this alpha is indicative of the impedance of the eddy current circuit, so it depends upon the aluminum disc. Okay, the properties of the disc will determine what is the value of alpha. Okay, and similarly you also have the a similar effect happening in the current coil also. However, in this current coil, phi s is in phase with I, ES lags these vectors by 90 degrees, and IES lags EES by alpha. Now the effective torque, since we have assumed that these torques, the two torques are in opposition, the effective torque would be, the deflection torque would be proportional to phi p phi s into sine of the phase difference between these two fluxes, and alpha being the power factor of the eddy current circuit. Okay, so you have cos alpha here. Now sine of this is delta minus phi. Okay, so that is the eventual deflecting torque that is being produced. Okay, and the braking as is given by this dampening magnet. Okay, and ignore this control spring here. I'm just indicating it so that to indicate the braking mechanism. Okay, and the braking torque is generated because the aluminum disc is moving in the field of the electromagnet. So the braking torque would be generated because of the EMF being produced. The EMF is proportional to the speed at which the conductor is moving in the magnetic field. Okay, and so it is E is proportional to phi m, which is the strength of this magnetic field, and omega, which is the speed of rotation of this aluminum disc. Okay, now if we say that R is the resistance of this eddy current path, okay, then there is the current that is produced, that is E by R, and again that can be written in this manner, and eventually the braking torque, the effect is given by tau b, where if the if the permanent magnet is placed at a distance r from the center of this disk, the effective radius is as r. Okay, so the braking torque eventually is proportional to phi m square into omega by r. Okay, so what is important is that the braking torque is proportional to omega. Okay, and when the instrument is operating in steady state, the braking torque will be balanced by the deflection torque. So if the deflecting torque is tau d, then the speed of the rotation, okay, is directly proportional to the deflecting torque, and if the deflecting torque is proportional to the power, then we can say that the speed is proportional to the power, and so the number of rotations will be proportional to the energy being consumed. Okay, so what you have to make is that the tau d should represent something. Tau d should be made proportional to the actual power being consumed by this circuit. Okay, so another point is that this, for the meter to be reliable, the indicated quantity should be constant. So K1 and K2 are anyway constants. So phi m is the strength of the magnetic field, that should be constant. R is the effective radius of the disk, and if the permanent magnet is kept at a fixed distance from the center of that rotating disk, then that is constant. And we also need this R, the resistance of the eddy current circuit should also be constant. Okay, so the strength of the magnetic field and the resistance of the disk are kept, should be made constant for the meter should to be effective for long-term usage. And in order to decrease the amount of current that is being dissipated, amount of heat being dissipated, we want to reduce, we have to keep R to the minimum, and therefore you would have aluminium as a preferred choice of the disk material, so that the resistance is minimized. Okay, and by choosing the radius to be slightly large, we can make the speed of the disk to be kept also low, so that the number of revolutions that are required to indicate 1 kilowatt hour, say, is also minimized. This also would be helpful in, so this will also indicate reduce the possibility of other errors due to friction. If you keep omega to be low, so the meter constant, if it is made low, that is also helpful in sort of minimizing the chance of some type of errors caused due to friction. Okay, now let's go further into the mathematics of this. So we've already seen that the deflection torque. Now we want the deflecting torque to be proportional to the power. So that was the indication, that was the conclusion that we've seen in the last slide. the deflection torque is actually proportional to the flux in the two coils, sine of delta minus phi and cos alpha. Okay, and phi 1 was V by Z, proportional to V by Z, and phi s is proportional to I. So in effect, the deflecting torque is proportional to V I sine of delta by phi cos alpha and this impedance of the pressure coil, that is Z. Okay, now if we are sure that the frequency at which the energy meter is being operated, if that is constant, then we can be sure about the impedance, the value of the impedance and cos alpha. They can be made constant. So if we are sure about the frequency, then we can say that tau d, or we can say that tau d is actually proportional to Vi sine delta minus phi, or tau d is equal to some k2 times Vi sine delta minus phi. Okay, and we have the braking torque being proportional to the speed of the rotation. So braking torque can be said as some k times n, where n is the number of rotations per unit time, and from which we can calculate n is something that is proportional to Vi sine of delta minus phi. What we really need is that this should be where the number of rotations per unit time, okay, should be actually proportional to Vi cos phi. Okay, so what we basically need is that delta should be 90 degrees. Then the speed of rotation will be proportional to the power, and the number of rotations over some time will be indicative of the energy being consumed. Okay, and the true value is registered only when delta is 90 degrees. However, by merely connecting an inductive circuit to the supply voltage, you cannot bring a 90-degree phase lag. Okay, so you need to do something more. So for this case, what is done is that a additional lag coil is added in that arm of the magnet close to this disc gap, and this lag coil will produce an additional lag, and that will bridge this gap. So if you have this delta, this is V and this is phi, okay, this is phi pt here. So here phi p is a further lag of theta is added, so that these two are at a gap of 90 degrees. This lag adjustment, let's go a little more into that. Okay, now let's describe this. Now you have a voltage V connected across the pressure coil, and this V is causing a current IP which lags by delta. Okay, this is generating a MMF A TPT. Okay, and consequently a flux phi pt. All of them lag by delta with respect to the voltage. Now phi pt, due to the construction of this core, is split into phi g and phi p. And phi p, where phi g is bypassing this air gap and phi g goes through this disc. Sorry, phi g bypassing the air gap and phi p goes through the disc. Okay, now there is a lag coil here that is wound across this arm through which 5p is going. Okay, and this will produce an EMF EL, okay, induced in the lag coil, and due to this impedance of this lag coil, there is another current IL produced in the lag coil. Okay, let's say gamma is the angle between EL and this current in the lag coil, that is IL. Now this current also interacts with the core, and it also produces a lag MMF of 8. Okay, so there is residual, that is there is 5pt minus 5g, that is from this, that flows through this gap, and also an additional resultant from this MMF in the lag coil. Okay, so these two components, this component result in this 5p. Okay, so and by tuning the lag coil, we can make this phase lag, the additional phase lag, in a manner such that this delta plus theta will become 90 degrees, and this flux is in exact quadrature with the supply voltage. Okay, one another very important aspect that is encountered in motor meter is the friction, because contrary to indicating instruments, in case of motor meters, the friction is ever present. So it has to be taken a little more seriously. So friction can occur in two types. One is the static friction, that is friction that is present when the moving part is about to start revolving. So when it is about to start to revolve, we are basically talking about very light load or low load conditions. Okay, and this may indicate that due to the static friction, when a small rate of rotation is expected, what you end up with is zero rate of rotation. So therefore, to compensate for it, it may be needed that you need to add a constant small compensating driving torque into the system, so that this static friction can be sort of contracted. And when you have a static friction, you also have the running friction. Okay, and this is the friction that is proportional to the speed of the moving system. Okay, and this is added to the braking, and this is caused due to the other moving parts like the indicating mechanism, the drive gear train and everything, that would add to this running friction, and this can be reduced by making those designing those parts in a manner such this friction is reduced. For example, by using jewel and pivots, say, to support the disc, okay, and using bearings to reduce friction in other parts, okay, and reduce contact surfaces, okay, etc. Okay, now let's see the, so as we have said, in the static friction, okay, when there is light load, there may be no movement at all because of the static friction. Okay, and this is compensated by adding an additional coil that is a little off-centered from the pressure coil. So whenever the system is energized, there is an interaction and there is a torque that is produced due to the EMF generated by this coil, by this compensating coil, and this will give an asymmetric torque, and because of that a slight mm, rotating torque is being slight deflating torque is being generated. Okay, and due to the torque, this is tuned in a manner such that it just compensate for the static friction. And this is a picture where you have this compensating coil. Okay, on the other side, you can also have creep present in motor meters. What is creep? Creep is that whenever there is you'd see that the meter is energized by two coils: the pressure coil, the flux in the pressure coil, and the flux in the current coil. Okay, so it may happen that even when there is no current, there is a flux in the pressure coil. Okay, ideally this flux should not be producing any torque at all. The flux alone should not be producing any torque. However, since it is always energized, it can interact with some other current flowing through the circuit, and there may be a very slow rotation of this disc. Okay, and this is called as creeping. And this is compensated by drilling off-center holes in the aluminum disc, in the rotating aluminum disc, and whenever this hole comes directly below one of the poles of the shunt magnet, the rotation stops. So here you have the compensation for creep. You have a hole here in the aluminum disc. Okay, and just like the case of the polyphase wattmeter, you can also have polyphase energy meter. Okay, where you have different assemblies and the deflection of the assemblies are added up to give an overall reading. Here we have a three-phase, two-element energy meter. Okay, and just to complete, we have we come to the recording of the indicating mechanism. So you have this aluminum disc, and this is the spindle of the aluminum disc and you have a worm gear on this disc. This worm gear meshes with this gear, which picks up and transforms the rotation onto this gear train mechanism. Okay, the gear train mechanism is again shown here. Okay, there are multiple gears, and these gears would be connected to various dials in case of an analog meter, and these dials will indicate the exact energy reading, okay, as an integrating instrument, and they form the readout. Okay, however, these are all that we have seen until now, until this slide. They are talking about analog energy meter. Okay, however, in more recent times we have digital or electronic energy meters being in usage, and they do not have any mechanical parts, and using dedicated chips, what is being done is both the current and the voltage, the magnitude of the current and voltage are being measured, and the phase difference between the current and voltage is also estimated, from which the power generated in one cycle, the power consumed in one cycle is estimated, and then that is being integrated over time, added over time to get the energy. This, as we had done, that this will basically make the assumption of what the supply frequency is, and for each supply cycle you have vi and phi being estimated, and the power being consumed is taken as vi cos phi into the time uh, time period of the supply. Okay, and so in the electronic energy meter you don't have any mechanical parts, and the display is also digital in nature. Okay, and towards the end, these are the chapters that would give you an idea for further reading on the energy meters. And with that, we come to the end of this presentation. Thank you for your patience.